Most traditional computational fluid dynamics engines work from the outside in. Computational fluid dynamics, or CFD, is the use of applied mathematics and computers to model fluid flow. These traditional engines apply an invisible hand to a macroscopic mesh, simulating bulk fluid behavior while completely ignoring the quantum and atomic mechanics occurring underneath. Arc Lake approaches this problem from the exact opposite direction. It operates as a rigorous, multi-scale computational chemistry environment designed to build physics from the subatomic level up. Instead of applying a global force to a volume of liquid, this engine calculates fluid behavior by generating forces from the atomic core and pushing them outward. Here in the Arc Lake Chemistry Lab interface, you can see how this operates in practice. We have the 3D molecular canvas displaying the structure, sitting directly alongside the dense orbit delta node editor and periodic table panel to manage the underlying logic. For researchers requiring true physical fidelity in their simulations, treating a liquid as a generic geometric mesh is insufficient. The simulation must recognize that a fluid's macroscopic behavior is entirely dependent on its microchemistry. To achieve real-world large-scale CFD, Arc Lake dictates that all physics must propagate neutron first. Large-scale CFD refers to computational fluid dynamics applied at real-world scale, simulating massive volumes of interactive particles. Data flows in a strict unidirectional path. It originates at the neutron center, expands outward to the proton, and then sequences through the surrounding electron orbital rings. That internal atomic logic continues pushing completely outward, eventually dictating the macroscopic physical states of the entire simulated environment. Managing this architecture requires a highly idiosyncratic nodal matrix to link the complex math and physics operations required at each step of the propagation. By mastering this subatomic unidirectional data flow, a researcher can verify exactly why a macroscopic fluid behaves the way it does on screen. This is the orbit delta node editor, configuring how atoms construct molecules. We see node connections between curium and osmium. Atoms interact through precise links routed between specific electron orbit shells, like K, L, M, and N. These connections act as Rydberg-like sockets. A Rydberg socket is a computational framework aligning mathematical operators with energy pulses to handle data allocation between elements. Drawing these manual shell-to-shell connections establishes the foundational computational logic that will govern the entire chemical compound's physical behavior. Once drawn, the engine resolves the interaction using a rigid computational sequence, completing all logic before advancing to the next simulation frame. Because the node structure is this granular, every single molecular bond in the simulation can execute distinct, highly customized behavioral instructions. By defining interactions at the specific orbital shell level, the simulation avoids the data homogenization that frequently plagues standard particle physics engines. To process data, the engine uses a strict 12-tier execution logic. The framework centers around the input-output gate and 3 foundational blocks. The pipeline has 2 rigid phases, beginning with 6 mathematical operators and concluding with 6 physical attribute operators. During the first phase, the engine resolves the algebraic sequence. It strictly prioritizes geometry and parentheses before moving down through arithmetic. Looking at the teal parameters, the second phase activates. Only after the math is fully resolved does the engine allocate physical states. A value passes downward through a rigid physical hierarchy, calculating mass, then volume, weight, density, temperature, and finally ending at velocity. The cardinal rule of this architecture is that mathematical geometry must always precede physical manifestation. Decoupling the operations and strictly sequencing the math before the physics creates a deterministic, highly calibrated baseline that inherently prevents the simulation from exploding. The next challenge is scaling this deterministic atomic logic up to accurately measure chaotic, non-symmetrical macroscopic phenomena, like fluid wakes. Within the Arc Lake environment, a fluid wake is formally defined as a finite arc, a non-symmetrical, chaotic geometric curve. To measure these finite curves, the software employs a specific geometric method known as the arc edge theorem. The measurement finds the maximum boundary, the largest circle failing to fit inside the curve. Next, the minimum boundary, the smallest finite circle at the origin. Finally, it isolates exactly 1/8 of a circle circumference, perfectly mapping the chaotic curve's symmetrical folding point. Extracting this 1/8 geometric symmetry effectively converts a chaotic, unpredictable fluid shape into a measurable, deterministic data unit ready for processing. At this stage, the symmetrical 1/8 circle measurement provides a numerical value with undefined units. To be useful in chemical research and large-scale CFD, these undefined units must be mapped to real-world physical metrics. The user configures this mapping within the CFD settings by specifying the exact target metrics required for the simulation. The available parameters range from standard metric and imperial scale systems to specific measurements like pascals for atmospheric pressure or meters per second for wind velocity. Once the desired metric is set, the Arc Edge tool continuously translates the geometric curves into these units, feeding the updated, quantized data directly back into the simulation loop. Quantifying chaos through geometric symmetry allows researchers to simulate previously unpredictable macroscopic fluids while maintaining strict mathematical fidelity to the underlying atoms. All of this atomic nodal logic ultimately manifests at the macroscopic level in the large-scale CFD engine. The final critical calculation step in the ArcLake pipeline is the crosstab sigma integration. The sigma integration is a function that mathematically aggregates the total values across all active node operations into a single cohesive output. Once the atomic and molecular operations fully resolve within a specific scene tab, the sigma function sums the total calculated force. This aggregated sigma force is then applied directly against the master CFD environment variables, as seen here in the Scene 1 parameter readout displaying arc edge factor, scene gravity, and scene pressure. The sigma integration ensures that an interaction happening at a single electron shell accurately ripples outward to influence macroscopic factors like wind velocity, temperature, and custom gravity parameters. We can now trace the complete ArcLake pipeline, observing a seamless connection from the neutron core up to a massive fluid wave. Every single macroscopic fluid particle in this simulation is invisibly governed by the strict 12-tier operator stack processing its internal math and physics. This rigid neutron-first propagation model stands in stark contrast to standard industry tools that prioritize bulk rush deformation over actual chemistry. ArcLake operates entirely outside the boundaries of a standard 3D visualization suite. It functions as a highly calibrated computational laboratory. By forcing physics to propagate strictly from the atomic shells outward through a rigid mathematical pipeline, ArcLake provides a deterministic environment for testing real-world chemical fluid dynamics.